Friends, I welcome you all for the last year of your graduation. As you have opted chemistry as a subject for the last year, you have to learn four different papers of the chemistry: physical chemistry, inorganic chemistry, organic chemistry, and analytical chemistry. I would say you are more familiar with physical chemistry, inorganic chemistry, and organic chemistry since you are learning this since 11th standard. And for analytical chemistry, you are a bit less familiar with since you are studying analytical chemistry right since SY level. At SY, you learned about scope and importance of analytical chemistry. You learned about classical methods of analysis such as gravimetric analysis, volumetric analysis. You learned certain separation techniques like solvent extraction and introductory part of certain chromatographic methods as well. Then you studied certain instrumental techniques such as pH metry, potentiometry, conductometry. You had the study of statistical treatment of analytical data as well. But I would say there was a more focus on the classical techniques. But TY onwards, so up to PG, there would be a more focus on instrumental methods of analysis, instrumental techniques involved in the analysis, which are more sophisticated techniques. Now I would be dealing with optical methods, unit number 3 of analytical chemistry paper for this particular semester. So let us go through the syllabus of this particular unit. The first instrumental technique, that is the atomic spectroscopy, in which we are dealing with two instrumental methods: flame emission spectroscopy, abbreviated as FES, and atomic absorption spectroscopy, abbreviated as AAS. In this particular topic, we have to study introductory part, energy level diagrams, atomic spectra, absorption and emission spectra. Then with respect to flame photometry, we got to learn principle involved, instrumentation. Again, with respect to atomic absorption spectroscopy, we have to learn principle and instrumentation. Then how can we make use of these two techniques for quantitative analysis? With the help of four different methods such as calibration curve method, standard addition method, internal standard method, and ultimately we have to compare these two techniques, flame emission spectroscopy and atomic absorption spectroscopy. And then we have to see the applications, advantages and limitations as well. Now next one is the molecular fluorescence and phosphorescence spectroscopy. We have to study introductory part of this and principle involved in both these methods. Then we have to learn the relationship of fluorescence intensity with concentration. Then factors affecting fluorescence and phosphorescence, instrumentation involved in both these methods and applications of these two techniques, comparison between fluorimetry and phosphorimetry, and comparison of both these methods with the absorption techniques. Ultimately, the scattering studies such as turbidimetry and nephelometry, introduction of both these methods, principle of both these methods, then factors affecting scattering of radiations such as concentration, particle size, wavelength, refractive index. We have to learn instrumentation of both these methods as well as applications. So let us go through the FES and AAS. Flame emission spectroscopy and atomic absorption spectroscopy. Flame emission spectroscopy is also known as flame photometry. Now these two are very important techniques as most of the alkali and alkaline earth metals can be quantitatively analyzed from the body fluids by using these two techniques, flame emission spectroscopy and atomic absorption spectroscopy. In fact, these two techniques are widely used for soil analysis, water analysis as well. Now both these are atomic spectroscopic methods. Now, what do you mean by atomic spectroscopy? Let us see. When atom is provided with the thermal energy, then electrons of atoms are getting excited from lower lying energy level to higher energy level. So we would say atom undergo excitation. Now this excited electron come back to ground state or lower lying energy level by emission of radiant energy. This could be considered as de-excitation of atom from upper energy levels to lower energy level by emission of radiation. If these emitted radiations, emitted quantas are analyzed by the spectrometer, then we will be able to get emission spectrum consisting of lines. These lines are a characteristic of the element present in the sample. In case of atomic absorption spectroscopy, gaseous atoms when exposed to radiations, these gaseous atoms absorb the wavelength characteristic to them and they undergo excitation, and remainder of the quantas are transmitted. These transmitted quantas are analyzed by the spectrometer. You will get dark lines corresponding to the quantas absorbed. So that is nothing but the emission spectroscopy and absorption spectroscopy. Now we got to see what is the energy level diagram. Now see, in case of sodium, we have valence shell, that is the third one, and valence electron is present in the 3s orbital. So that 3s electron can be excited to 3p orbital by gain of thermal energy. When that electron comes back to ground state, that is 3s level, it emits the quantas having wavelength 589 nanometer and 589.6 nanometer. In case of potassium, the valence electron is present in the 4s orbital. If potassium gaseous atom is provided with the thermal energy, then that 4s electron gets excited to 4p orbital, and while coming back to ground state, that electron emits radiations or quantas having wavelength 767 nanometer and 769 nanometer. So this is something related with quantized energy levels. Is during excitation, whatever the energy gained, that energy is emitted during de-excitation of atoms. So that is the basis of both these techniques, flame emission spectroscopy and atomic absorption spectroscopy. Now we got to learn about flame emission spectroscopy or flame photometry in detail. First of all, we shall see what is the principle involved in this particular method. See, suppose you are with the salt having formula Ma with M plus as a cation and A minus as an anion. Say for example, say sodium chloride. So sodium chloride has M plus as Na plus, Cl minus as A minus. If that aqueous solution of sodium chloride is introduced into the flame, it is provided with the thermal energy and it undergoes evaporation, leaving behind Ma solid particles. These Ma solid particles again gains more energy and they undergo vaporization to Ma gas. These gaseous molecules of Ma gas gains more energy and undergo dissociation to M gas and A gas. These gaseous atoms are developed, of which gaseous metal atoms gain thermal energy from the flame and undergo excitation, as I already discussed with you. These valence electrons are getting excited, and that state is represented as Ms state in the gaseous state. If that state is highly unstable, electron being excited come back to ground state, and while doing so, certain quantas are eliminated, quantas are ejected, having energy hν. If these emitted quantas are analyzed, you will get lines in the spectrum. So these are the different events occur when aqueous solution of the sample or a metal salt is introduced into the flame. Let's sum up all these events again. So first event is the evaporation of aqueous solution to form the solid metal salt. Solid metal salt undergo vaporization to give gaseous molecules of metal salt. Gaseous molecules of metal salt undergo dissociation to give gaseous metal atoms. These gaseous metal atoms gain thermal energy from the flame and undergo excitation to excited gaseous metal atoms. Highly unstable excited gaseous metal atoms will coming back to ground state in quantas. So these are the four events which occur when aqueous solution of metal salt is introduced into the flame. Now whatever the energy that is lost during the de-excitation, that energy is equal to the energy gap between ground state and excited state. And that energy is nothing but h nu, where h is the Planck's constant and nu is the frequency of emitted radiations. We know that nu is equal to c by lambda, where c is the velocity of light, lambda is equal to wavelength of emitted radiations. So therefore that equation can be hc by lambda is equal to delta E, or hc by lambda is equal to E2 minus E1. Now the number of excited atoms present per cubic centimeter can be calculated from Boltzmann equation, which is derived from statistical thermodynamics. The equation is n asterisk by no is equal to a e raised to inside the bracket minus a by kt, where no is the number of ground state atoms, n asterisk is the number of excited state atoms, a is the constant of a particular element, E A is the activation energy, A is the Boltzmann constant, and T is the temperature of the flame. The above equation indicates that number of excited atoms depends upon the temperature of the flame. The power gets decreased at higher temperature. So overall result is at higher temperature of the flame, number of excited atoms are more in number. So that indicates how the temperature is significant to increase the number of excited atoms. At higher temperature, more number of atoms are getting excited, so more number of quantas are emitted. So emission intensity caused by sample when introduced into the flame depends upon the flame temperature. Not only the flame temperature but also the concentration, but we'll be dealing with that particular aspect in the forthcoming lecture. That's it for this session. See you next time with the additional information regarding the flame photometry. Thank you very much.